All right, so welcome to those of you here. Maybe you can all say hi. Hello. It's a party here for those of you remote. You're missing out for sure. Also, welcome to those of you who will be joining asynchronously. All the folks who will be watching this on YouTube. Please remember to like and subscribe or whatever they say. You all should have gotten the syllabus. I'm going to start here. I printed out copies in case anyone wants one. Would you rather digital? Yeah, for sure. Okay. Pass these around. And so you're here. You're in ME712. This is applied mathematics and mechanics. I'll talk to you about what that means and what we're going to be doing. But first, some of the more basic stuff. Basic stuff being, if you're coming to class, then it's in photonics, 11 to 12:45. If you're coming on Zoom, then here's your ID. Hopefully you're already here. If you're joining on YouTube and you want to join in the future synchronously, you can simply email me and I'll give you the password if you missed it in the email I sent out. Office hours. So there's really no office hours in the traditional sense. We can't come to my office, but we can jump on Zoom. So I'll be on Zoom Tuesday afternoons, basically right after class until like 3 o'clock. But I know that for some of you, there are significant time zone issue challenges there. And so for that, I can't figure out how to kind of pre-plan when we can meet. So my thought is we'll just set up a time via email. If there's something you want to chat about, excuse me, we'll use the same Zoom ID, same password, and we can meet via Zoom. I'm pretty flexible, so whenever is going to work for everyone. If there's a time you want to meet, even if it's just something brief, just send me an email, and we can jump on Zoom and chat about stuff. I'm not too worried about the prerequisites. I assume if you're here, you've probably taken something like linear algebra, differential equations. If you haven't taken differential equations or you took it a long time ago and you don't use it that much, I'll try my best to kind of remind you of some of the various important topics. We will likely get into one topic that you might have covered in differential equations, so we'll kind of, I'll talk about that in a minute. If you're learning asynchronously and you're watching this on YouTube, then there's a YouTube channel for us that is here. This is just a playlist of where all the lectures are going to go. So after each lecture, most likely each day, I will post them tagged onto this playlist. And so either you can rewatch them if that's helpful, or if you missed a class, you can get caught up by watching these YouTube videos. Let's see here. So what else is going on? So what is this class, I guess? So this class is meant to give you some of the mathematical tools that will hopefully help you throughout your PhD. Some of your master students, this will help you in applying these techniques to other courses you'll be taking, or learning some ways of doing things numerically or analytically that can help you in whatever you do in the future. So my goal with this class was to be able to construct and solve models for things that are happening around us. I put the emphasis on mechanics because I'm not a trained mathematician, but I'm someone who uses applied math in my research all the time. It kind of forms the backbone of most of my research. My research is primarily in solid mechanics, sometimes fluid structure interactions. And if you do anything in solids or you do anything in fluids, one of the things you'll learn right away is that we know the governing equations, and they're a remarkable challenge to solve. And so what this class does is try to provide you some ways to approximate solutions, understand what the dominant physics are in your problem. It's not a numerical methods class. It's more of a, how do we construct a model? How do we test the model? How do we approximate a solution? And that kind of gives rise to the two things that I think make up this class. One is kind of understanding and giving you all an overview on the necessary mathematical tools. And that's kind of how I laid the class out. So dimensional analysis and scaling, this is what we start with. It's easy. I personally believe this first section of the class should be taught to undergraduates first or second year. If you've seen some of this before, which I suspect you have, that's fine. I'm mostly introducing it so that way we're all on the same foot, and it helps with some stuff later on when we start to non-dimensionalize complex equations. It kind of can be helpful to all of us be grounded with some of this dimensional analysis. So that part I think is pretty straightforward. I'm going to try to go kind of quickly through it, and so feel free, obviously, if there's questions to stop and ask them. But we'll probably get into stuff that might be less familiar to you after that. So one of those things is perturbation methods, which is, okay, you have a problem, you can't solve the equations, you want to understand how things are behaving. And so what you can do is you can approximate your solution around a certain point. So that might mean like, well, I know the simplest problem, but what if I want to add in some of the more complex things to it? How do I add them in a way where I can still solve something? And the perturbation methods are a way that allow us to do that. I'm new to this semester teaching this class, is this topic on linear stability analysis. This is something I've wanted to add to this course for a couple of years now, but finally, I think I've trimmed enough stuff to make room for it. That's something that you might have seen before if you've taken a class on like nonlinear dynamics, chaos, or if you took, depending on the teacher you had, for something like a ordinary differential equations class, you might have discussed some of these topics. And so I will try to kind of introduce them generally, and then maybe talk a little bit about applications of stability and solid mechanics problems. I work a lot on like buckling, wrinkling, and instabilities in thin structures. But there's also plenty in terms of like hydrodynamic stability, transition between flow states. So linear stability analysis is something that'll be new this semester. Variational calculus is something that I suspect most of you have not encountered before. If you have, great. This is a way where we can use mathematical tools to find the governing equations we want to solve. And so that'll be, it's kind of if you've never heard of that, it's basically a kind of different flavor of mathematics. It kind of builds on some of the ideas in perturbation methods, where you're kind of taking a system and you're perturbing it a little bit and using that to derive the equations you want. And the last topic is on differential geometry, which is rising in utility and popularity in mechanics research. So solid mechanics people are using differential geometry to study curved structures, shells, objects that are going to deform from flat to curved. It's really useful to work with being able to do calculus on curved surfaces, which is what differential geometry is. People doing fluid mechanics research, if you're doing things with bubbles or droplets, again, you're dealing with curved manifolds or curved menisci, things like that. And if you're coming from more of like the robotics side, there's a lot of increased utility of things like non-Riemannian geometry and differential geometry to kind of map like robotic swarms, things like that. I'm going to try really hard to kind of keep these mathematical tools tied to problems that are kind of relevant to people studying mechanics. To me, that means things like kinetics, diffusion, various problems in continuum mechanics, solid mechanics, fluid mechanics, kind of providing examples and ways of working things through that connect to things that you might encounter in your research. I think the goal, I like to kind of specifically outline what the learning outcome is. Like, I want you to leave this course being able to derive and analyze mathematical models. I also kind of think that this course should provide you the ability to, particularly if you're a PhD in mechanical engineering, undoubtedly you will come across a paper that seems relevant to your work or interests that you can't read. You should try, and it's just not, there's things that you didn't learn that they assumed you learned. And my real kind of layman's goal for this course is to give you the ability to, if there's a paper like that you can't read at the beginning of this course that you can read at the end. And so along those lines, we're going to do things, class problems like homework assignments, where we'll work on problems that are related to mechanics. But also, I'm going to kind of give out some kind of important papers and that utilize some of these applied math techniques that we'll kind of read and then discuss in class. Both of those things, I don't know how they'll work in a half remote, half in-person thing. Usually the way I've done homework in the past is I have volunteers from the class go through their solution. Usually they come up to the board and write what they did and explain what they did. And that's kind of how I approach grading, which is more of a, I want to see your thought process than your work. I want to see you explain this stuff, because I think if you really understand something, you can, that's when you're able to teach it to someone else. And so I really value that communal working on problems. I'm not sure how that's going to go, so we will try. Maybe I'll share screens, or I don't know. There's a midterm exam, which is basically a long take-home problem set. And there is a project at the end that is really geared towards finding a paper that you would like to understand or that is relevant to your research. And to me, that's kind of where that final goal hits home, where I want you to, see if you can apply the techniques you learn in this class to understand a paper. And the final project is really a presentation in which you're explaining some paper to the rest of the class, and you're kind of talking about how that paper utilizes various techniques that you learned to solve the problems there. We'll talk more about those as we get further, but that's kind of the general outline of this class. It's much more hands-on, trying to work through problems. In terms of texts, I have not found a book that I think covers what I want to cover completely, so I put a bunch of recommended texts. You don't have to purchase all of these. If you're doing stuff and you're like, oh, this is what I like, this is great, I want to keep working on problems like this, then you're going to want to pick up some of these books. If you're like, oh, maybe I'll get one. If you're going to get one, I would get the one that's called Introduction to Foundations of Applied Mathematics by Mark Holmes, unrelated. Also, because of the strangeness of this semester, I've decided to type up my class notes. That's an ongoing process that I started over the summer, and so I'll show you what that looks like. They're on my class website, so if you go to here, it's bu.edu/moss/courses, and scroll down, ME712, Applied Mathematics and Mechanics. It's got our syllabus on there in case you lose it. It's got a link to where these lectures are on YouTube. I can't put the Zoom link on the website. I have been Zoom bombed in the past giving a seminar, and that was a remarkably unpleasant experience, and so I'm going to not risk that again. Before I show you the notes, we're going to utilize Mathematica quite a bit in this class. If you're familiar with Mathematica, great. If not, also fine. I will kind of walk you through. We spend basically like half of a lecture where I basically go through how to use Mathematica, from like the most basic things you could do to some more complicated problems. And I also have, that I'll be posting on the website as we get further along, Mathematica notebooks that you can download and use either to like build off of or for reference, stuff like that. So those will be posted kind of as we need them. But I would recommend anytime soon to download it. You get it free as a BU student, so all you have to do is go to the link that's on the website. That should take you to where you can download the student version. So I would do that soon and open it up. If you've never used it, it is different. It's weird. A lot of students are kind of like, I'm really great at math at MATLAB. Can we just do MATLAB? And I like to think like if you're doing applied math, this tool will pay off for you in the long run. And it's kind of like you can if you want to you have a nail that you need to hammer into a piece of wood, like you can use the back end of a screwdriver, but like you might want to just use a hammer. And to me, that's like the MATLAB Mathematica analogy. Like, yeah, like a lot of the stuff we're going to do, you can use MATLAB for. It's going to be messier and painful, and the power of Mathematica is everything's done symbolically. And so the math looks like the math you're writing down on your paper. And so you get the same equations. You can plot things without, you know, defining a Lin space where you have to tell it what you want to plot your equation over. I think if you trust me and take a dive into Mathematica, it will pay off in the long run, and I'll try to help you through that process. So my notes are here. So if I click that link, it would take me to here. You can download this if you want, but I would recommend just like going back to the website and going to this link, because what I've linked to is the file that I'm updating on Dropbox. And so as I'm adding new things, it's going to be the most up-to-date version will be the one on the website. So feel free to come back as much as you want. Right now, as you can see, I've gotten through kind of chapter 1 and started chapter 2, so I've got work to do. But if you want, you can read ahead. This is basically what I'm going to cover. This is my way of writing it up, so you can kind of see, like, this is going to be today's lecture once we get going. I've also included throughout, this is probably, and I'm going to do this throughout the rest of the notes as well, example Mathematica code that you can kind of type in to solve the problem. To me, this is a big deal. When I was learning how to do these problems, I would get to the point where I would read a paper and I would understand what they're saying and I would follow the equations, and then I would get to a point where I can't like reproduce the graph that they're making, or I can't get the simplification the way they got the simplification. So it's really important to me to kind of show you the kind of behind the scenes stuff, and so that's what I find Mathematica to be powerful for, and that's going to be incorporated in these notes. As you can see here, this is Mathematica code. It looks awful, but it'll make more sense once you get used to it. Let me go back to the syllabus. This stuff on the second page is probably pretty boilerplate and familiar language. It's about academic honesty, working together. To me, we often work together in this class, and I support that. I don't think this is something where I need you to be independent. I think in terms of both thinking through the complex problems and also implementing them in something like Mathematica or just by hand can be really tricky. And so I find it useful to work together. So if you do on a homework assignment, just tell me. If you do on your, if you do on various parts throughout the semester, just let me know. Obviously, this is a strange time. So you have kind of your COVID requirements that are university-wide, and this is kind of my way of reminding you of what those are. But beyond that, I think this is a stressful time, emotionally, mentally, just a kind of across the board full slate of things. Some people are far from home and they can't get back home. Some people are at home, which is more stressful than being far from home. Just let me know. And you don't have to let me know everything. You just let me know what you feel comfortable letting me know, and I can help work through things. I don't think this class is too burdensome in terms of what what I ask of you to complete. It's much. I think it's probably burdensome in kind of wrangling the complicated concepts. And so as that becomes more difficult throughout the semester, just be in touch with me, and then I can do what I can do to help you do that. People who are not standing in front of me but are over here, hello. Feel free. I think you all can you all unmute yourself? Can you say hello? Is that?
Hello.
Hi.
Hi.
Hello.
People in the boxes over here, and so I think that if you're comfortable, then I would say it would be useful to me and the rest of the class for you to just kind of interrupt and shout out a question the same way you would if you were sitting right here. If you don't feel comfortable, you can type in a question in the chat box, and and if you want to, you can send that anonymously as well, and I can try to monitor that. But I would welcome you to just kind of interject and interrupt. Anything from like questions about the course content to technical stuff like I walked too far away from the microphone, you can't hear me anymore, or hopefully you can see what you're supposed to be seeing, which I think you can. I think it's working. You can see the syllabus page right now. So yeah, please jump in whenever you'd like to ask various questions. And I guess now is the first opportunity for that. What questions do you have for me about the way the course is going to be laid out?
Do you have any preference between cameras on or cameras off?
So I don't. I have heard various feedback and been kind of monitoring how people talk about this on social media. I don't have a preference. I know that some classmates feel like it's really lacks community if you're kind of unable to see each other, but I don't know. To be honest, I would say just do what works for you, and that's fine with me. So, and that's true even if you're gonna jump in with a question. Like as long as I can hear you, I'm cool with that. So, no preference.
Okay, thank you.
Other questions? I will. I didn't mention this. I will also on the website. So what's going to happen is I'm going to lecture on here. It's going to look like this. And the result of this will be a PDF. And I will post the PDF on the website. So that same spot will have kind of each lecture's PDF. If I am delinquent and slow in doing that, just someone ping me, send me an email. I will not be offended. I just know myself, and I will forget to do certain things. So just let me know if the notes are not available.
So it's in addition to the course notes on the website?
Yeah, exactly. So you should have on the course website my typed up lecture notes, which is kind of like how I would do this if I was just giving you a book to read. But you know, as you know from taking courses over the way this is going to be delivered, we'll do different things. I'll answer questions that get asked, and so the notes will be a little different. So I'll post these as well, just so that way you have them if it's useful. But just remind me in case I forget.
Are you recording the Zoom?
I am. I hope it is recording. I got a red light here. I think it's working. Yeah, it's recording. So.
And then that's the one I guess.
And this will be the one that's on YouTube. I will cut out the first 20 minutes of me being a Luddite with computer tech. Yeah, just save the greatest hits, basically. Any question I answer wrong, I'll just like delete it out. Yeah. Other questions? Let me shut the door. I'm not yelling into the hallway. All right, should we get started? Should we do some stuff? Like I said, I find this first part to be very familiar to people and very straightforward. I do think there's some kind of fun things that you can, and kind of powerful things, like sneaky powerful things you can do with dimensional analysis and scaling. And that's kind of why I start here with like a pretty good foundation, because a lot of this course is geared towards, you have a set of equations, you know a problem that you want to solve, how do you solve them, how do you approximate them? But as someone who has been doing research long enough, there are definitely times when I'm working on a problem and I don't know what the governing equations are. Like I can kind of guess that maybe this should satisfy this or that, but it can be really helpful to just, how can I know the physics, I know sort of what's happening, I know what matters. How can I use that knowledge to learn something? And that's kind of what I think dimensional analysis can do for us. So we'll start there. And we'll start super basic, which is There are 1, 2, 3, 4, 5, 6, 7 fundamental dimensions. Does anyone know what they are?
Length, time, length,
That's 3.
light,
Yeah, that's a good one. Most people forget that one. Candela is the like luminosity of light, the measure of luminosity.
and maybe temperature.
Temperature, yep. Charge. Yeah, so for charge, it's usually current. So, yep. I think we're just missing one. What's that?
No.
So I'll write these down while people are thinking. So we have length. I'm putting a square bracket around the symbol to denote that right now I'm talking about like the dimension itself. And you'll notice that I'm not talking about like SI units or that doesn't matter. I'm actually talking about the fundamental concept of a unit of measuring something. And these are units of measuring something that for the most part are independent. You can't measure length by measuring time or you can't measure luminosity by measuring current, something like that. So the idea is that these should be independent dimensions. So we use L for length. M for mass. T for time. We said candela, which is usually denoted with a capital J, and that's for luminosity. Temperature, which has the annoying symbol of capital theta, but it does because T is taken. We have current, and we're still missing one more. Current is usually denoted with the capital I. And I'll show you why these symbols matter in just a second. Anyone know what the last one is that we're missing? It's one of the two trickier ones. Candela is the other. Anyone study chemistry much? You want to know?
Radiation?
Say that again?
Radiation, just as a guess.
Oh, radiation. That's a good one. I wonder what radiation would fall under. I think it would fall under
Luminosity.
yeah, either temperature or luminosity. That's a good question. Now I have to look that up. But that's not the one I was thinking of. But now I have to figure out where that would be accounted for.
Is it moles?
It is moles, yes. So we're looking for the amount of something, and that's what a mole denotes, the amount of substance. So for the sake of this course, we will primarily deal with length, mass, and time. Sometimes temperature, so maybe I'll highlight temperature as well. But the concepts are going to apply for all these, and so you'll see what I mean with that in just a second. But the idea here is that you can learn something by just thinking about the dimensions and using dimensional analysis. And then you can go ahead and say, I'm going to use the SI units to solve my equation, because that's how I'm going to measure things. The actual system of units is really saying, like, what tool am I going to use to measure length? Well, I'm going to measure length in blank. But before you even get there, there's plenty you can do just by thinking about these fundamental dimensions. And to demonstrate that, I'm going to go towards a problem that is something you probably solved in either high school physics or maybe first year undergraduate physics, which is the height of a projectile. And we're not going to solve it using calculus just yet. This is the problem of you have a ball, and you're going to throw that ball up in the air, and you're going to ask, how high is that ball going to go? And so, assume you know nothing about Newton, and you know nothing about either force balances or principle of least action or whatever kind of underlying philosophy will allow you to derive these equations, you could say, what matters? I'm trying to figure out how high a ball is going to go. So the height of the projectile we'll call x sub m, which would be the maximum height x that the projectile goes in the air. And we would expect that the maximum height the ball goes up in the air is going to be a function of some variables. And we can say, what do we think matters? So what matters?
The mass.
So maybe the mass matters. Maybe
Gravity.
gravity, that's got to matter, right?
Initial velocity.
Initial velocity, perfect. And you can go beyond that. You can say, well, maybe air resistance matters. You know, if you've taken a first year physics class, everyone just kind of ignores air resistance. And we're going to talk a little bit later about how to kind of properly ignore stuff. Like that's a big part of dimensional analysis and scaling is actually putting what you neglect on a more solid foundation and understanding how do you bring back it. So say you want to first figure out how high the ball is going to go. If you neglect air resistance, and then you say, well, let me add some air. How does air resistance change it? How do we add that back into the problem? That's a lot of how we will talk in detail about how you can do those types of things. But for now, we can just say gravity, the mass of the object you're throwing, the initial velocity. Those seem like things that might matter. We don't know for sure. It might turn out that initial velocity doesn't matter. If you've done this problem before, you know it does. But the point here is when we start with something like dimensional analysis as a way to understand or get some intuition for a problem, our goal is not to derive the exact equations. When we're doing something like this, our goal is to gain physical fundamental insight into the problem. And what that means is our goal is to develop a testable hypothesis. We want to come up with an equation that says the maximum height should probably go like this. I'm going to go in the lab and I'm going to change the things that my model says matter, and I'm going to see if my model works. And so the goal is to come up with a testable hypothesis. And we'll talk a little bit about kind of how precise we want to be with stuff like that. But for right now, let's say, okay, let's just assume we don't know what this function is, f. We think that it matters based on gravity, mass, and velocity. And we want to use these units as our guide. So how do we do that? Well, we can kind of come over here and say, let me write this instead as I expect those variables to matter in some combination. So some combination of multiplying or dividing by those parameters should give me a predicted maximum height. And so what we'll do is we'll write this in a more general way where we kind of are looking at the units. So we're going to just write and say, let's look at the units of that maximum height. And we know that you can only add like items. You can't add temperature plus mass. You can't have an equation in which you're adding terms in that equation that the units don't match up. So we know that the units on the right-hand side of my equation have to match the units on the left-hand side of my equation. So if the units on the left-hand side are the maximum height, the units on the right-hand side are going to be some combination of those three things. So it's going to be something like whatever the units of gravity raised to some unknown exponent. Gravity could enter as gravity squared or gravity cubed or 1 over gravity. So we'll just call that A times mass. Oops, I switched these around, sorry. Just so I don't mess up my notes, I'm going to switch them here. M to the A, so mass to some unknown exponent times initial velocity to some unknown exponent times gravity to some unknown exponent. You can always do this. You can say, I'm going to assume that like these things that I think drive the physics of my problem can be combined in some way. And the way they'll be combined is dictated by the exponents of these terms here. So what you can do now is you can say, well, I know the units on the left-hand side of my equation. I know that that is units of length. And then I can look at each term. And I can say, oops. I'll move down a little bit. And I can say, so this is, the units on the left-hand side is a length, obviously, a height is a length. That has to be equal to something with the units of mass to the letter A. Velocity, what's in the fundamental dimensions, how do we write velocity?
L divided by T.
Exactly, so we'll take the length divided by time to the B. And gravity? L divided by T squared. And so you'll notice that on the left-hand side, I have length to some known exponent. On the right-hand side, I have a bunch of dimensions that are dictated by the parameters that we think matter to some unknown exponents. We can collect these, and we can say, all right, I'm just going to look at M, L, and T. So if I do that, well, M only enters once, it enters with A. L enters in a couple times, and remember, when you are multiplying something that has exponents, you're going to be summing those exponents. So it should look like L to the B plus C. And now we'll take time. Oops, yeah, no, that's right. And then we'll take time. Time appears in the denominator in both cases, so both of the exponents here are going to be negative. So we would say it's going to be to the negative B minus 2C, because it's squared in the third term. And just to be like really pedantic and extra careful, we can also write the left-hand side of the equation to include mass and time as well. Or we could say, well, I can come over here and say, well, this is really just length times mass to the 0 times time to the 0, right? Those are both really just 1, so we can always multiply by 1. And so now you see that we have mass on each side, length on each side, and time on each side. And so what we end up having here are a system of equations, 3 unknowns, A, B, and C, and 3 equations, 1 for each of the 3 dimensions, length, mass, and time. All right, so what do we do now? So we can come over here and we can write out those equations. So we can write out the equation for length, and we can say, well, the equation for length should just be, if I look at just the ones that involve length, I have on the right-hand side, just taking the exponents. On the right-hand side, I just have B plus C equals 1. B plus C equals 1. So this would be the exponents of the term on the right-hand side of the equation underlined in red, and then 1 because the length appears on the left-hand side raised to the first exponent. We can do the same for time. Time is going to be negative B minus 2C, which equals 0. And mass is the easy one. Mass is simply A equals 0. In this particular problem, I chose this one because it's pretty straightforward. You have 3 equations and 3 unknowns. You know how to solve these. You pick one of the unknowns, you solve the others. And so what you'll find, we know that A is already 0, so we just really have 2 equations and 2 unknowns. And we know that we can write, so if A equals 0, we can solve this to find that B equals 2 and C equals negative 1. Okay, so now we can go back to our equation, which is that x is some function of these things, and we can insert our exponents that we found just from dimensional analysis to find that my maximum height should vary as the initial velocity squared. And I'm going to write a little symbol here. I'm going to use this throughout. So right now I'm going to write this symbol as a 1 tilde. And what that means is that there are some unknown numerical constants or parameters that I'm leaving out. We're going to ignore them for right now. We'll talk about them in a second. We're going to ignore them for right now. And so this is what's referred to as a scaling analysis. We know how the thing that we're interested in varies with the parameters of our problem within an order of magnitude. So I can tell you that it should scale if I change the velocity in this way or change gravity in this way. This is how I expect the maximum height to vary. And I can predict that pretty nicely within an order of magnitude. I'm not going to know that it actually is going to be 0.75 times this parameter. We'll talk about that in a second. But for right now, I have found that mass doesn't matter. So we thought mass mattered. That was our hypothesis. Doesn't matter. All that matters is the initial velocity. And the initial velocity is raised to the b. B is equal to 2. So this is initial velocity squared. And gravity is -1, which means it's over gravity. You can quickly check that squaring the velocity, squaring length squared over time squared, divided by gravity, which is length per time squared cancel out, you're left with a length. Your dimensional analysis works, and you end up with a prediction for the maximum height of your projectile without doing anything, doing any calculus, doing anything other than just kind of guessing what matters and then looking at the dimensions. And this is really powerful because we can now have a pretty straightforward way of figuring out what that unknown constant is. So what does that mean? So a more exact way to write this equation would be to say, well, I know there's some number there. So I know that really xm should be equal to some unknown constant, so I'll call it alpha, times b naught squared over g. And I might want to know what that unknown constant is. So at this point, there's two things you could do. We could turn to the actual problem of a projectile, and I'll do that in a second to kind of motivate the things we do when we approximate. Or you could just simply say you didn't know what the equations are that matter. You could simply run one experiment. Take a ball, throw it up in the air with some initial velocity, measure how high it goes, do it again at a different initial velocity, so double it. And our prediction says that if I double the initial velocity, I square that to 2, this is going to give me a prediction of how this would go. But I can just simply rearrange this equation and solve for alpha and try to determine what that numerical constant is by just running 3 or 4 experiments. You can't really change gravity that well, so you might as well change initial velocity. And you can very quickly, empirically, determine the complete relationship between these parameters. Yeah?
Let's say if the right-hand side of the equation should be in the exponential, can we still write it down?
Yeah, great question. So, in general, no. Because what happens when you have something that's either a log or an exponential on the right-hand side? What happens is you can only take the log or the exponent or the exponential of a dimensionless quantity. And we're going to talk in the next example about what happens when some of the parameters enter with dimensions, like v squared over g, and then some of them you only end up with the dimensionless product. At that point, it might enter as log, it might enter as exponent, and you don't know. You can't determine it using that because the ratio of the parameters form a dimensionless product. And there's still lots you can do with that. But you'll be unable to discern the something like if it appears as a logarithm because the quantity you're interested in appears dimensionless. So it's not only do you, when you have something like that, it's not only do you not know how that the dimensionless product is, what you're really after is trying to understand what is the function of that dimensionless group? And that function might be log of that dimensionless group, or it might be simply polynomial, but you still can't determine it. And so we'll talk a little bit about that, and still how this problem can be useful. This approach can be useful even if you have something where that'll happen. But that's a great question. Yeah, you'll be unable to determine if it appears as a log or exponent, because the thing that's in the log of the exponent is dimensionless, which is where this type of approach breaks down. Other questions? So I'm going to just quickly show you how you would solve this equation from the calculus approach, just to kind of motivate and talk about some of the things we do when we solve problems that we take for granted. And so you can combine Newton's second law with the law of a gravitational field to write down the governing equation for the height of a projectile. And this is something that might be familiar to you. It'll look like, hold on, it's too big. It should look like x double dot of t, where the over dot is simply saying that we're looking at the time derivative So this means dx by dt squared. So it's the second derivative of x with respect to time. This is going to be equal to negative gr squared, where r here is the radius of Earth, times over r plus x squared. This is probably not the equation you solved in high school or undergraduate physics, and the reason is this term, this ordinary differential equation is ordinary because I'm only taking derivatives with respect to one independent variable. I'm only taking derivatives with respect to time, so this is an ordinary differential equation. That's good, not that hard to solve. It's second order, that's also good, not that hard to solve. You know that if it's a second order ordinary differential equation, you need two, in this case, initial conditions, because this is something that's what's called an initial value problem. So we are interested in what happens at the initial state. We can write down those initial conditions right now. We know what they are. We know that, for instance, let's assume the ball starts at rest. So it starts maybe on the ground. So we know maybe its position on the ground at time 0 is 0. So its height initially is 0. And then we know that we have to throw it with some speed. You might notice that this equation doesn't have initial velocity in it, and that's because the initial velocity enters as an initial condition, which is that x dot of 0 is equal to my initial velocity. So here I have a complete problem. This is pretty straightforward to solve once we take care of this thing I highlighted in yellow. This thing I highlighted in yellow is what makes this equation nonlinear. And nonlinear problems are significantly more difficult to solve than their linear counterparts. They behave in strange ways. They will not necessarily have a unique solution. They might not have a solution at all. So you might have to think about existence and uniqueness theorems that you probably learned about in a differential equations course. They also can exhibit strange behavior where you might find bifurcations or things losing stability and something's working when you have one initial condition, but a different initial condition doesn't work anymore. We'll talk about that. We're going to talk a lot about how to incorporate this nonlinearity in a little bit. So we're going to, for right now, make the same assumption that you've made in years past and say, well, okay, what is this thing? well, this term here, that's the pain, is the radius of Earth plus the distance that we threw our ball. And this is the term that makes our equation hard to solve. So what do? Well, we could say, well, I know a little bit about this problem. I have some intuition, and I know that I'm pretty good at throwing a baseball, but not throwing one to a height that is relatively on the scale of the radius of Earth. So it seems pretty reasonable to say that compared to the radius of Earth, the height that I throw this ball is going to be really small. So why don't I just approximate this and say, do I need to consider this small extra term x that I'm adding to it, since I'm going to throw the ball 20 feet up in the air and the radius of Earth is like 6,000 miles or something. So we'll just say, why don't we approximate this as r? Just say that x is really small compared to r. So that ratio is really small. So I have a big number plus a really small number. Why don't I just say it's the big number? And then this problem becomes a lot simpler, because now I have simply x double dot of t. This r is squared. That r squared cancels out with the other r squared, so I'm just left with negative g. Now that's a pretty straightforward differential equation to solve. You have two initial conditions, you integrate twice, apply the two initial conditions to find the two unknown constants of integration, and you solve this problem and you end up with this solution that probably looks familiar, I think, which is that the height of the ball as a function of time is simply 1/2 g t squared plus v naught t. Oops. Pretty good. Okay, we still haven't connected this back to what we just did with our dimensional analysis, so let's try to do that. So what does that mean? Well, I'm going to put this away and draw over here and say that I can plot this. I can plot time over here. I can plot x on the y-axis. That's always a little bit weird to see, but it's the height of the ball is what x is. And the height of the ball is a function of time. What goes up? It's going to come down, so it's going to go up. It's going to be a parabola. It's going to come back down. How do you know it's going to be a parabola? Well, our equation says it's going to be a parabola. It's polynomial there, second order. And so it'll do something like this. And we can kind of go over here and say, well, this might be what we're interested in. This is our maximum height, xm. And the maximum height xm occurs at some time tm. How do we find the maximum height? This is just reminding you of some basic calculus. If I want to find this point, set the derivative equals 0, so I just take x dot. Now I know what x is, so it's easy to take the derivative. Set that equal to 0 and solve for my maximum height, or solve for the, actually what you'll be doing is solving for the time at which the maximum height occurs, and you plug that back in to figure out the maximum height. So if you do this, the time at which the maximum height occurs is v naught over g. Therefore, which is what my little 3 dot symbol means, therefore, plug that back into the original equation, and what I get is that x sub m is equal to v naught squared over 2g. And so what that means is that we can analytically derive that alpha is 1/2. So it should be of order 1, which means that my numerical prefactor for a scaling to hold. So for something where I can say, oops, this with this scaling notation here. What I'm saying, as just a reminder, is I'm saying that equation should work, and as long as we assume there's some numerical prefactor that's of order 1, which means it's not smaller than 1/10, it's not larger than 10, it should be somewhere in the middle there. We have a prefactor of 1/2, and so that's pretty good. We did okay. So using calculus, we quickly confirmed our scaling. So I think it's kind of nice because, for one thing, we didn't have to do any math with that first step. We didn't have to do any calculus. We didn't have to remember to take the derivative of our equation. But the bigger point is, a lot of times you can't solve these equations. A lot of times it's not simple where you can just write down the exact equation you want, solve it analytically, and end up with a closed form solution. So the point of this dimensional analysis is that it allowed us to get really close to the right answer without doing anything other than looking at the dimensions, saying that the dimensions on the left-hand side have to equal the dimensions on the right-hand side. How do the dimensions on the right-hand side enter the problem? And we got most of the way there. The other reason I wanted to bring this up is the way you typically solve that problem over here, and in particular, the assumption I made right here, is kind of heuristic. Like, this is a problem that we all have some intuition for. Like throwing a ball up in the air and comparing the height that it's going to go to relative to the height to the radius of the Earth is something that we can all say, well, yeah, obviously the height's not that high. There's two problems with this. One is you might have a differential equation that you don't fully understand the parameters that might be small, and how to neglect them. And a second problem is you might say, well, okay, yeah, I know that I can solve this problem by assuming this thing is small, but I kind of don't understand what the nonlinearity is doing. So what's the nonlinearity doing in this equation? What does the nonlinear term mean?
It's the distance from the center of gravity.
Yeah, and so physically, what happens as the distance from the center of gravity gets larger?
The force of gravity decreases.
Yeah, exactly. So do you expect that as your initial velocity increases, this is not just for you, this is for anyone, do you expect that as your initial velocity increases, the ball will go higher or less high? As the effective gravity decreases because the ball is getting further away from the center of mass, the ball should either get higher or less high, or stay the same, I guess. Should get higher. And so that presents an interesting problem. I mentioned how these nonlinear problems have weird things. Well, we know from, again, SpaceX and NASA that there is a velocity that I can shoot a rocket up into the sky, at which point it will not come back down. And that rocket is satisfying this equation. And so that nonlinearity is saying, yeah, we are assuming physically that our gravitational field is uniform for all x. And that's not correct. Our gravitational field isn't uniform. Our gravitational field depends on the distance between the object and the center of mass of the larger object. So we lost any ability to talk about that nonlinearity with any subtlety. We basically said, nope, it's always small, let's get rid of it, and we're done. What we're going to do going forward is two things. One is formalize the way we can approximate things. So in this case, it was easy to say, x over r is small, let's get rid of it. Going forward, we're going to find a way of saying, okay, what is actually the small parameter? And how do we get rid of it? And then what happens if we want to bring it back in and understand, okay, let's add some of that nonlinearity back in. Maybe we're not going to shoot the rocket up so that it leaves the gravitational field of Earth, but maybe it's going to go up high enough where that nonlinearity is going to contribute to our prediction of how high it goes. And maybe we need it to stay below some certain height so that, because we're putting a weather balloon at some particular height in the atmosphere, and we want to be pretty sure about where that goes. Well, then we need to understand how to incorporate the nonlinear effects of this term more systematically. These are all things that we're going to be doing going forward. A lot of the techniques we're going to be learning are going to allow us to do that, account for this nonlinearity. Check to see how our problem behaves as we kind of define and vary this small parameter. So this kind of helps motivate some of what we're going to do going forward, which is how do we do this more formally, especially for problems that we don't necessarily have the intuition for. If you end up doing research in which you use these applied math skills, you're going to come across a problem where you're like, I don't really know how the convection of this particle compares to the streamlines of my flow. Like, I don't have a good sense for if this defect is small compared to what. And so it becomes really important, because either at that point you have to just throw up your hands and not solve anything, or start to make some assumptions. And we're going to talk a lot about kind of how to do that properly. All right, what questions do you have so far about any of this?
I don't understand why the approximation we made on the first part should be in the same order. So alpha can be like 100.
Yeah, that's a great question.
I'm sorry, just what was the question? We can't really hear it from Zoom.
I'll repeat that. So the question was, why are we expecting alpha, that unknown constant that's multiplying our v squared over g, why should that be roughly of order 1? And my kind of hand wavy, kind of soft answer to this is that if it's not, typically you're missing some other physics in the problem. And so typically that prefactor is usually of order 1 because all the dominant physics are entering at order 1. And so usually anything that you're neglecting would enter at what's called a higher order, which basically means like that model is not going to give us the exact answer because we neglected a term which is going to have a small correction to it, and that correction is going to enter at a different order. So it should be of order 1 if our scaling captures all the important parameters of the problem. And if it's not, if you have something where it doesn't, you generally left something out in that initial approximation. So like over here, when you said maybe it's just this, you generally missed something. And I've had this happen before where like we had a scaling that we derived. We were saying this really, when I say this problem, it sounds really strange. We took a thin sheet of plastic, put it on a surface of water, and poked on it. And it makes a bunch of crazy wrinkles. And the first time, I remember, the first time I tried to figure out, like, well, how many wrinkles does it make? I wrote down a scaling, and I ended up with something that seemed like it sort of worked, but my alpha was like 12,000. and I was like, oh, great, whatever, it works. And then my PhD advisor was like, I think something's probably off. And we kind of went back and realized that we were kind of missing this one term that changed the scaling a little bit, made the data fit better and collapse nicer, and also the prefactor kind of went back to 1. It didn't matter too much for the range of things I was trying to predict, but if I had tried to extend my model to a different set of experiments, maybe a different material or a different length scale, then my model would have failed. And so oftentimes when you derive one of these scalings and you have a prefactor that seems a bit large or small, you might find that your scaling works for your problem, which you might say, oh, we're done. Oftentimes, I found that usually if you try to extend it, it doesn't work beyond kind of those parameters, and that's usually a good red flag that something is off. Other questions? How are energy levels? How are we feeling? Especially those just kind of staring at my whiteboard. Should we do another? Would it be worthwhile? We have some time. Well, let's do another, because this will get at the question of what happens when. Well, let me put it a different way. This will get at the problem that we talked about with having the inability to discern logs and exponents and other things. So if there's no other questions, I'll move on to another problem we can use this exact same technique for. Which is to study the drag on a sphere. So the drag is a really important problem. If you don't do anything in fluid mechanics, and you might be unfamiliar with why we would care about drag. Drag is the force that's essentially slowing something down as it's moving through a fluid, whether that fluid is air or liquid. It's a crucial design parameter for designing automobiles, racing bikes, ships, and the idea usually is you want the drag to be as low as possible. So we want to know how the drag depends on the various parameters of our problem. So here's an example of one where you might be able to do what we did before and write down how the drag force should depend on various things by your own intuition. Or you could also look at the governing equations of fluids, the Navier-Stokes equations, and kind of identify, all right, there's a viscous term, there's a length scale that corresponds to the size of the object. We expect the density to be in there. We know that there's going to be some velocity of the fluid that's going to matter, or the velocity of the particle relative to the velocity of the fluid. And either way is fine. You can arrive at how you think the drag force should matter. If this part here, this idea of figuring out what matters based on your intuition is kind of disconcerting to you, we're going to do a problem probably at the beginning of next class where I don't know what the governing equations are. We're going to try to just use our intuition to figure them out. And hopefully that'll be a way where you can kind of see how you can kind of play with dimensional analysis, because the mathematical rigor is not that intense, so you don't have to know at the outset that everything's right. So what matters for drag on a sphere? Well, either from your intuition or from the governing equations of fluid mechanics, you would know that what matters is that drag will depend on the radius, which we'll call r, the velocity, v again. What else do we have? We have density, which I'm writing down as rho, looks sort of like p, and viscosity, which we'll write as mu. This is our dynamic viscosity of the fluid. Okay. Again, if it's not obvious to you that those are what matters, that's okay. You can turn to Navier-Stokes to kind of see where these terms enter into equations, or you can wait and we'll kind of talk about how you can start from scratch and test the model on your own. We'll do that in next class. So we'll call the drag force d sub f, which we expect to be a function of those things I just wrote down. R, V, rho, and mu. We'll do the exact same procedure. We'll just kind of map this from kind of our unknown function f to something with our dimensions. So again, I'll use this square brackets to say I'm thinking about the dimensions of this object. Should be equal to my radius to the A, my velocity to the B, my density to the C, and my, oh, what happened there? This guy went to sleep. That's okay. Let me just plug it in just in case. Those at home, can you still see and hear me and see my screen? You probably can, I guess. It's just the people in the class that can't. Ha! We didn't see, they see that? Who saw that coming? The people here can't see anything. All right. Let's get this thing booted up. Oh, come on. All right. Give me 1 second. Is anyone still there? Hello? Probably not. Oh, not there. Okay. I know you're dead. Come on, computer, come back. All right.
They can hear you. Maybe it's kind of slow.
Can you all still hear me, or did you lose me at home?
No,
I
we
can hear you.
Okay, cool. So it's just everyone here. That's okay, actually. We'll figure this out. That's all right. We'll get it. So, all right. Well, we're going to do the exact same thing anyway. So if you can't see, this says that the units of the drag force should go as the radius to the A, velocity to the B, rho to the C, and mu to the D. And we're going to do the exact same thing. So what are the units of force? Newton. So what are the units of force in the fundamental units?
Less times length divided by times squared.
Yes, perfect. So we know that this is mass times length times time to the -2. Radius is length. So it should be L to the A. I'll keep trying to get this thing booted up. It is not behaving. Velocity is length over time, so it's going to be length over time to the B. Density is mass per volume, so mass per length cubed to the C, so this would be M per length cubed to the unknown exponent C. And dynamic viscosity, that one people sometimes forget, is mass over length times time. So it would be mass over length time to the D. Okay, so for the sake of time, I'm going to do this again where we solve these unknowns together. We still only have 3 fundamental dimensions that enter the problem. They are length, mass, and time, so we expect to have 3 unknown equations. There's 3 equations. But you already can see the problem. The problem is we have 3 unknowns, length, mass, and time. 3 equations, 1 for length, 1 for mass, 1 for time, and 4 unknowns. We have 4 unknown exponents. So even before you start, you can imagine that things are going to become a problem here. So let's just try it anyway. We can write that L Actually, before I do that, let me do one more thing, sorry. I come over here. Let's take a moment and just combine these terms to make our life easier. So that means it should be length enters a bunch of ways. It enters length to the A plus B minus 3C minus D. So that's kind of a mess. What else do we have? We have time, which enters as minus B minus D. And then we have mass, which enters as C plus D. And then on the left-hand side, we already see that mass enters to the first power, length enters to the first power, time enters to the 1 over second power. And so now we can go through and use our same procedure as before to say we have an equation for length. The equation for length is going to be A plus B minus 3C minus D. A plus B minus 3C minus D is equal to 1. For time, I have negative B minus D equals negative 2. I'm going to move those over. And for mass, what do I have? I have C plus D equals 1. 4 unknowns, 3 equations. What are we going to do? For the sake of all of us being on the same page, obviously we could pick any of these unknowns to leave unknown. I'm going to choose D so that we all kind of do the same algebra. And if we choose D, then this leads to B is equal to 2 minus D. C is equal to 1 minus D. And A is equal to 2 minus D. And D remains unknown. Okay, so what do we do? Well, we just do the same thing we did before. We're going to put all these things back into here. And we'll see how that looks. Well, how does that look? Well, what happens if we put that back is that we find that D sub F will scale as R to the 2 minus D, velocity to the 2 minus D, density to the 1 minus D, and viscosity to the D. Okay, that doesn't seem particularly helpful. Well, what we can do is we can collect all the terms that are raised to the D and kind of separate them out as what we'll call a dimensionless group or a dimensionless product. And so what that means is we can write this as, this should scale as R squared V squared rho times mu R V rho all to the D. Does anyone work in fluid dynamics? Does this thing look familiar to anyone?
Wait, is that okay, so, sorry, I just slipped my mind. The dimensionless constant, Reynolds.
Yes, exactly. It is. It's upside down Reynolds number. So Reynolds number is RV rho over mu. So we found the dimensionless number, the Reynolds number, from dimensional analysis here. If we had solved for a different constant, we would have gotten the same dimensionless product, but we might have gotten it flipped upside down, where it would have been actually the Reynolds number appearing there, and you would have had slightly different prefactor to the Reynolds number. So this thing here is what's referred to as a dimensionless product or a dimensionless group. And these dimensionless products and dimensionless groups are usually given the notation, which when I was a student, I used to loathe, but now I've just gotten used to it or gotten over it, of capital pi. It comes from, it's, summing things. You would use a capital sigma to sum over something, but if you're taking a product, kind of a product, this equivalent version of a product, you would use capital pi. These are products that represent kind of thing quantities being multiplied together. So you end up with this dimensionless group, capital pi. We'll take it and raise it to the D right here. But typically, you're going to see us using capital pi for these quantities. And I'll remind you that in this particular case, what we just said, this quantity is, well, the Reynolds number, RE, is defined as R V rho over mu. So we arrived at our dimensionless product has the Reynolds number appearing in it. Unlike the last problem, we're not quite done. We have a little bit more to do here. And so we can again recognize that, well, okay, there should be some numerical prefactor here. And that numerical prefactor can enter as alpha times r squared v squared rho what do I call it, rho pi d. And the reason we're not quite done is because both of these quantities, this thing here and this thing here, are dimensionless. And that means that both of these quantities can enter in a variety of complicated ways. What do I mean by that? So what I mean by that is, while this is a solution, another solution is something like this. We can also write alpha 1 times r squared v squared rho pi d1, where that's some exponent. And then we could also add to that another one. We could say, well, there's no reason why we wouldn't expect. This is also a valid solution. We didn't change anything. The dimensions, all we've used so far are dimensions to solve this problem. So if the top one is valid, the bottom one's also valid. Because the dimensions on the right-hand side all add up to the same dimensions on the left-hand side, so you can keep adding them. And so what that means is we need to be a little bit more formal here. We can say something to the effect of our drag force should equal rho r squared v squared times alpha 1 pi d1 plus alpha 2 pi d2 plus so on and so forth until we get bored of writing that out. And what that means is this is an arbitrary function of alpha and pi d. And getting back to the question that was raised earlier, that arbitrary function could consist of logs or exponents in here. There's no reason. They would also lead to the same dimensional representation. So what we'll do is we'll just say, okay, well, I don't know how this thing enters, but I do know that there's some unknown function, f of pi, that I would be solving for. In the last problem, what we did was we had an unknown constant. And we said, well, we can run a set of experiments to determine what that unknown numerical constant is going to be. Here our problem is a little bit more complicated. We don't have an unknown constant. We have an unknown function of some dimensionless quantities. And so in this particular case, the goal would be to figure out, well, what's that function? So what you might do is take a sphere and put it in a fluid of some known viscosity and perhaps some known density, and vary the velocity and measure the drag force to see how that function f of pi changes. So in this problem, our simple experiment is a little bit more complicated. But again, all is not lost. We now can write the more complete version of this to be, do that over here. The complete version, we would say, okay, this is going to be equal to rho r squared v squared f of pi. And now our goal is to figure out what that f of pi means. If you do anything with fluid mechanics, you would know that this f of pi is complicated. It's really messy. So the function of how the Reynolds number depends on, for instance, so how if I was to draw something like f of my Reynolds number, oops, as a function of the Reynolds number, I have a really messy nonlinear result. It would be something like something that kind of starts to behave okay, plateaus, has a dip around the transition to turbulence, and then behaves in a really complicated nonlinear way. So that function is really complex. But you could decide, well, actually what I'm really interested in is a particular range of the Reynolds number. Again, we start to learn how do we approximate, how do we account for a small Reynolds number versus a large Reynolds number, how does that change the equations? But one thing you can do, and I'm going to end with this, is you can use this approach without doing anything more than what we've already done. You can use this approach to create scale models for your problem. So you could say, well, what I really would like to know is what the drag force would be on this ginormous sphere that I'm building, or this F-15 fighter plane, or this particular boat or mountain bike that I'm making. And what this dimensional analysis and scaling tells us is that we can run an experiment at a small scale, determine how my unknown f of pi varies with my Reynolds number, scale it all up, and that'll tell me what's going to happen on the large scale. So what does that mean? Let me show you what that means. So for instance, what you can do is you can say, well, let's use our model. Let's create a model. So I'll write this in purple. So let's run an experiment on a model system where everything is small. I can do that at home or in my lab on the bench, where I can say, I'll look at the viscosity of the model divided by the radius of my sphere in the model, the velocity, and the density. And I will set that equal to, so that, if you recall, that's our dimensionless pi. I'll set that equal to the dimensionless pi that I'm really interested in. This is the one that is the viscosity, radius, velocity, and density of the system that I'm actually going to use, the thing I'm actually going to build to scale. And just like you've learned forever ago with things in geometry, like similar triangles, where you can take a small triangle where all the angles are known and scale up that triangle to make all the sides bigger, and you'll still know that the angles are the same as you scale. That physical similarity between those, I should say geometric similarity between those properties. This is an example of physical similarity. So I can take this set of equations here. I can say, well, what I'll do is I will test let's say I'll solve for my velocity of the model to look like this. And what I can do is then fix all of these quantities. So I can just fix this viscosity, fix this size of the sphere. I know what things are going to be, what velocity I expect to, or what radius I want to make this thing at when it's bigger. I know what density it's going to be in, and I know what viscosity it's going to be in. And I can just simply run this, these experiments at a desktop scale and predict how this thing is going to behave at a larger scale, using the same concept as you would use for saying like triangles at a small scale to like triangles at a large scale. We'll have some geometric similarity. Whenever there's a scaling, and this is probably the most important point here. Whenever there's a scaling that predicts the properties of something, that implies that there is some similarity in the underlying physics. So this is what's referred to as a physical similarity. And we're going to spend a lot of time talking about similarity solutions, similarity variables, things that we can do when we know that something should behave similarly on one scale to another scale, and the ways that we can use these similarity variables to simplify problems. The next example we use that we'll talk about sometime either next class or the class after that is how to use a similarity variable to take a problem that's really complicated to solve and turn it into something that is really simple to solve. So these concepts of similarity are at the heart of dimensional analysis and scaling, but they also tell you that there's something really physically important about this problem, physically useful for you to understand. Whenever you see similarity popping up in one of your problems, it's an indication that there's something going on there that you can get a better handle of if you kind of frame the problem properly. I know I rushed there at the end. If you have questions on this, you can send me an email. We can schedule a time to jump on Zoom. I talk about this in more detail in the class notes that you can get the PDF for. So if this part feels a little rushed, you can jump online and grab the PDF and kind of read through it, and hopefully it'll be more clear. And obviously, just bring whatever questions you might have the next class. So thanks everyone. Thanks everyone who's joined online, and I'll see you all in some form next week.